Assalamu alaikum everyone, and thank you for joining this demo session. My name is Muhammad Usama Intizar and I will be guiding you through this 1 month intensive course on machine learning for chemists. My background is in technology and programming, and over the years I have worked on bridging the gap between computer science and applied fields like chemistry, data driven decision making, and research applications. I also do have experience in web development, app development using Flutter, digital marketing, and social media management. My aim is to help you as chemists take advantage of machine learning in a very practical and approachable way. You don't need to be a programmer to benefit from this course. I will walk you step by step from the basics of Python into the world of chemical, data driven, and then gradually into core machine learning and applied projects. This course is designed as a 1 month intensive program specifically tailored for chemists who want to integrate machine learning into their research and professional work. The idea is not to turn you into professional programmers overnight, but to give you the tools to understand, apply, and even build ML based workflows in your chemistry related tasks. Think of it as learning a new scientific instrument. Once you know how to handle it, you can adapt it to your field. The focus will be on practical understanding, hands on coding, and real world chemistry applications. By the end of this course, you will not only be familiar with the language of machine learning, but also be able to confidently apply it to chemical problems like property prediction, classification, and even reaction modeling. Okay, let's move next. And here we see the fundamentals difference between traditional learning, traditional programming, and modern machine learning. Unlike traditional programming that relies on explicit instructions, machine learning allows systems to learn patterns from data to improve over time. This adaptability this adaptability makes machine learning powerful for handling complex tasks where writing specific rules is challenging and impractical. Like machine learning handles complex patterns and predictions automatically. Like, let's just get an example in which we get a clear understanding what is traditional techniques, traditional programming, and machine learning. So, there is an office in which a coffee machine is placed for employees to get a coffee whenever they need it. So, an employee gets up, go to the coffee machine and press the button, and the coffee machine makes the coffee, and the employee takes it and goes back to his seat. Well, this is the defined rules. Like when we press the button, the machine's pre-programmed script starts running and it creates coffee. And there may be multiple flavors that the employees can select, like espresso. For example, if we take espresso, the employees presses the flavor of espresso and the machine makes it for the employee. So in the opposite scenario of this, where another machine is placed which is based on machine learning, it has AI capability like artificial intelligence, so it can learn from different scenarios available in its surroundings. An employee goes to that machine and the machine displays the text that your espresso is ready. The employee says, "Wow, I did not even touch the machine, but it made the coffee for me before I even could interact with it." So, what happens here? The machine understands that different people have different taste for their coffee, and for analyzing for past 30 days the machine created a relationship between flavors and the employees, and in that way whenever its camera sensor senses a new person it nearby approaching it, it creates a coffee of that flavor that is related to that employee. I hope this clears you the understanding of traditional programming and machine learning. The role of machine learning in modern chemistry. What is machine learning? I have explained it to you and with an example that is mostly in the physical robotic machines. But how can we use machine learning in modern chemistry? Machine learning has become a game changer in chemistry because it helps us make sense of enormous datasets that would take years to analyze manually. Instead of synthesizing thousands of compounds in the lab, machine learning models can predict which ones are most promising for drug discovery or material design. This dramatically reduces the trial and error process. It's not just about speed, it's about uncovering the hidden patterns. For example, ML models can a subtle relationship between molecular structure and their properties, allowing chemists to predict solubility, toxicity, or reactivity even before touching the lab bench. This saves resources, time, effort, money, and making it a highly practical tool for modern research. The first application of machine learning is accelerating drug discovery. AI techniques have accelerated the discovery of new drugs, exemplified by helicine, an antibiotic discovered using ML methods. Similarly, we know in 2019 there was coronavirus and the vaccination was for coronavirus was also discovered using AI. One of the most well-known successes in chemistry, which is helicine, was discovered by MIT researchers in 2019. So, how did AI help them? Instead of testing thousands of molecules one by one, they used ML to scan a vast chemical space and identified a compound with potent antibacterial properties. This was groundbreaking because it found a molecule unlike any existing antibiotic. This case highlights how AI can identify promising compounds faster than traditional methods. Similarly, AI methods significantly reduce the time and resources, as we discussed previously, needed to find promising drug candidates, predicting material properties faster than traditional experiments. Machine learning models can predict physical and chemical properties of materials more rapidly than experimental approaches, enabling faster innovation cycles in materials science. In material science, machine learning is used to predict the performance of new battery materials instead of physically making and testing hundreds of variations. ML can stimulate and suggest which materials are most likely to be stable and efficient. Similarly, toxicity prediction models can filter out dangerous compounds early, ensuring safety and saving costs before animal or human trials. Optimizing catalysis and reaction conditions. Machine learning algorithms help optimize catalytic processes and reaction parameters, improving yields and efficiency by analyzing large datasets to identify ideal conditions for different reactions. Reducing time and cost in research and development. By automating predictions and analysis, machine learning reduces the experimental workload, lowering cost, shortening development timelines in chemical research. So, the real world examples are like helicine, vaccination of corona. The best one is already, as I explained, helicine antibacterial antibiotic. The discovery of helicine showcases ML's capability to identify novel antibiotics rapidly, demonstrating the technology's potential in addressing urgent health challenges. AI models have successfully predicted the stability and performance of battery materials, accelerating the development of more efficient energy storage solutions, as I have explained in the benefits of ML in machine learning. These are some real world examples that are being used. Like you can see, before there was only lithium batteries, but now there are silicon and there are new encouraging batteries. Like China has been researching more advanced batteries that can last up to 50 years without even recharging. Machine learning for toxicity prediction and compound classification. ML methods enable accurate toxicity assessment and classification of chemical compounds, improving safety, evaluation, and regulatory processes. It also keeps us safe from different harms like the burnouts during the chemical reactions. We can save ourselves from that. Before even we go to the lab, we can predict what will happen under different conditions for a similar reaction. This course is structured to build step by step like climbing a staircase. It is divided into 4 weeks, similarly, 4 modules, like one module each week, each focusing on foundational knowledge, core machine learning concepts, molecular representations, and applied workflows, providing a structured learning path. In week 1, which is basically module 1, we will be we will focus on foundations, understanding the basics of Python and chemical data. This ensures that even those without programming experience can keep up. Foundations are critical. We start by asking what is machine learning and why does it matter in chemistry. Here we will set expectations and collect ML concepts to familiar chemical research problems. Next, we will cover essential Python essentials, like we also need to learn some basic Python which will be used in ML that connects to chemistry. You don't need to be a software engineer for this, like you don't need to be a Python expert. Just knowing variables, loops, and functions is enough. get started. We also introduce you to Jupyter notebooks, which is very helpful in writing machine learning codes using Python as well as notes besides it. Finally, we work with chemical data handling, chemical data formats like SMILES and SDF, giving you practical exposure to real datasets. Week 2, Module 2, Core Machine Learning Concepts and Practical Skills. Week 2 introduces the fundamentals of machine learning, such as different learning paradigms, evaluation matrices, and how to use libraries like scikit-learn. This module covers supervised and unsupervised reasoning, learning, regression techniques, and model building with machine learning libraries like scikit with hands-on exercise. In this module, we will go deeper into the foundations of machine learning. You will learn about different types of learning like supervised and unsupervised, as well as the third one, which is reinforcement learning, and how these apply to chemical problems. For example, predicting solubility is supervised learning, while clustering compounds is unsupervised. We will then introduce the essential libraries like NumPy for maths, pandas for handling datasets, and scikit-learn for machine learning models of chemistry. The hand-on session will focus on building a simple regression model such as predicting boiling points, so you immediately see ML in action. I will also be showing you a quick overview of these models in the end of this demo session. Week 3 dives into chemistry specific ML concepts, how to represent molecules in a way that computer understands. In this module, focus is placed on molecular descriptors, graphical neural networks, SMILES notations, and comparing molecular representations. The way we represent molecules is central to applying in machine learning. Molecules are not just numbers, they are graphs of atoms and bonds. In this module, we will learn about descriptors, fingerprints, and how to compute them using RDKit. For example, descriptors like molecular weight or topological indices give computer numerical ways to represent chemistry. We will also be seeing an example for this in the end of this demo using real Python code. We will also introduce graph neural networks, which directly use the graph structure of molecules, and for this we will be using a Python library which will create different graphs for us. This is cutting edge, but we will keep it simple and intuitive. You will also see how SMILES, string, and 3D conformations are used in machine learning. By the end, you will compare multiple molecular representations and understand which works best for different tasks, like I have already explained. Finally, week 4 is where everything comes together. We apply machine learning to real chemical problems like bioactivity, classification, clustering, and even basic reaction prediction. This final week emphasizes real-world applications. Classification problems are everywhere. Predicting a compound is toxic or bioactive is one of the most practical use of machine learning in chemistry. We will also explore clustering and similarly analysis, which helps in drug design and chemical space exploration. Reaction prediction is another exciting area. While full reaction modeling is complex, we will be touching you the basics with templates and reaction fingerprints. Finally, we will cover how to save, deploy, and share model. This ensures your work is not just an academic exercise, but something reproducible and usable in research. Okay, here comes some practical demonstrations using Python language and machine learning models for chemistry to get you an idea. The first example we will be going through is the analyzing of ethanol's molecular structure using Python tools, reinforcing data handling and visualization skills. This demo shows how Python and chemistry meet. We take a simple molecule ethanol and represent it using its miles notation. With just a few lines, maximum of 5 to 6 lines, we can compute important properties like molecular weight and log P, a measure of hyperphobicity. The idea here is not to master our kit. Oh, sorry for moving forward. The idea is not here to master our kit in one go, but to give you a flavor of how chemical data concept connects with programming. Later in this course, we will take these computed descriptors, feed them into machine learning models, and predict new properties. This small demo illustrates how coding empowers chemists to explore molecule computationally. So let's go to our coding site. Okay, here is a 6-line code with some comments. We will be using rdkit as library, and we will be importing different classes from it, and we'll be using it to determine molecular weight and log P for ethanol. So let me just run this file, and we can see that we got molecular weight of ethanol, which is 46.069. Similarly, log P minus 0.0014. And we did not even provide any values here. We just provided the Smiles notation for ethanol, and we got molecular weight and log P. That is also mentioned in outputs. Okay, let's get back to our slides and see what's next. Okay, we will be training a machine learning model to predict boiling points of hydrocarbons, applying regression techniques practically, and checking solubility of different compounds. In final projects, like I have already mentioned, solubility prediction, toxicity classification, compound clustering, and reaction outcome prediction. This allows us to apply everything we have learned. For example, you could build a regression model to predict solubility, which is crucial in drug design, or you could classify molecules into toxic or non-toxic categories, something highly relevant in pharma. Another project could involve clustering compounds into meaningful groups, which is useful in designing diverse drug libraries. Finally, for those interested in reactions, a basic reaction outcome prediction project can be explored. The point is, each project connects directly to real chemical challenges. Okay, before we go to conclusion, let's take another example of coding. Like I just shared with you an example of molecule analysis. We will now go to boiling points, and here you can see I have just around 60 or 50 lines. Most of them are simple print statements which are not included in The counting, so we just import numpy library, pandas, matplotlib for graphs, different graphs, and scikit-learn for different models like linear model, and from linear model we will be getting linear regression model. Creating data set, converting it to data frame, and then visualizing it using plotlib library, then preparing data and train model. Here we will be training the model using linear regression, and we will be seeing what the model learned. We will check this out, and then by using this learning we will be evaluating the model, like whether the result it's providing are perfect or not. So we will be using mean absolute error and r to square for that, r to score. And next, using this data sets, visualization, learning, and then at the end predicting new compounds. Here we will predict boiling points of nonane and decane by providing just the molecular weight of these two compounds. So let me just run this and we will see what's there for us. It's not just difficult. Don't try to understand this code for now, because it will just make your mind go blah blah blah. Just keep turn off thinking for now. Just focus on viewing the work of ML, the work of coding in chemistry. And here, after running the code, we have got our chemical dataset that we provided here. Compound, we provided methane to octane, and we got our data frame, which is in pandas library, and we got the relationship predicted by machine learning algorithm of linear regression. Here you can see this is the live graph, and we can zoom in, zoom out, we can scroll it away or up as we need. We can then save a screenshot, save the figure in different formats like PNG, PDF, WebP, and EPS files. Here it's telling us what it learned. It learns this relationship 2.82 multiplied by molecular weight plus minus 179.21. For every 1 gram per molecule increase in molecular weight, the boiling point increases by 2.8 degrees Celsius. Model performance. So we used linear regression, and what's the performance of this? The more value of R2 squared is near to 1, the more perfect it is. And at the end we predicted two compounds. Here you can see we provided the molecular weights of nonane and decane, and we got the boiling point of them, which is nearly around their actual values. Not pretty close like it should be, but we are getting these. Here similarly for decane, which is 174, but we are getting 2 to 1 because it learned this, and we provided just 8 compounds to learn it from them. The higher this volume, the better the prediction and better the results will be. So try to provide as much as large data sets so that machine learning can get better graphs of different relationship between different properties and then predict new compounds. After boiling point comes high throughput, like if we are working on 10,000 compounds, what will happen? If we do this physically in lab, it will take months, years to check different things. But while we are here, this is just some dummy data. But if we provide a file to it, like file from the internet, we can get a file. We will be using original files in the course lectures, but in this demo I will be using random values. I have created this screening data using compound ID, using random values, molecular weight which is also random, log P which is also random, activity score is also random. I provided this data to data frame of pandas, and then we can get number of compounds, number of properties, and then first 10 compounds I have mentioned here 1000, and we can rewrite it to 1000. And let me just run this and we will see what it provides. Here you can see it just took 1.5 seconds to provide us these results. First 1000 compounds, compound ID, its molecular weight, log P, and activity score. It just took 1.5 seconds for this. And even if I increase to 5000, here 5000, and rerun it, we will see it just took the same amount of time that it took for the previous one, and we got the results for 5000 compounds. It's showing us just 10 because this we are running this in the terminal. If we save this in the file, we will get all 5000 compounds in our list, in our file. And if we do this by hand, you know well how much time it will take. Similarly, for time and cost, okay, traditional programming versus machine learning, we will be checking this. And here the graphical view, drug discovery timeline, traditional versus machine learning enhanced. For target ID, traditional one take 1 year and machine learning takes half. Lead discovery, lead option, preclinical, then clinical, then approval. So here traditional takes 15 years of time while machine learning takes 10.5, which saved us 4.5 years, which is huge. But as AI is improving day by day, this time will increase. Like we will be saving around 10 years, maybe in 1 year. Like after 1 year, the AI will be as much enhanced that we will be saving 10 years instead of 4.5. This is just some representation of Plotlib so that we can get to know how can we use these graphs to show different values for our needs. Okay, next is semiconductor band gaps, which are used for material prediction, like for batteries, semiconductors. Okay, let's run this. Don't just try to understand. As I already told you, these are just some random values, and here similarly I have provided the data set, format it into data frame, print it so that we can see how it's in the pandas library, how it's saved for us. Okay, let me just run and we will check this. Here you can see we just printed this data frame like the data we provided it in a proper table form, and then we trained the model XMAT versus Y gap on x-axis and on y-axis. On x-axis we are using average atomic number and electronegativity difference, like which one matters most for band gap. And here we are using random forest regressor instead of linear regression. we are using different model, and show importance, like which one is important for us. And let me just show you the graph that we have just created here. This one, which properties matter most for band gap. I have dual screen, so the graph shows on the other screen. That's why I need to move it to the screen which is being shared with you guys. So don't think that it's already pre-made. uh, this terminal creates this one. So here you can see atomic average atomic number and electronegativity difference relationship with band gap of semiconductors. If I close this, average atomic number is this one and electronegativity difference is this, like so. Electronegativity difference is more important, I think, for band gaps. Let me just clear this and we can move then to solubility, which is like the most important ones nowadays in Pakistan especially. So let's just run this. I will be running this in hope without, like, there are steps to provide a realistic data set. I I am using random, as I discussed before. Random, random, random. All data is random. Then converting it to data frame. Then data exploration using different features: molecular weight, log P, hydrogen donors, hydrogen acceptors, etc. And showing this in different graphs of scattered graphs. We will be using those, and then we will be training our ML, our own model, using this data, using this relationship. We will be training our own model using sklearn, scikit-learn, which is used for learning purposes, and here we will be using k-neighbor regressor as well. So here for solubility we will be using linear regression model, random forest regressor, SVR, k nearest neighbors regressor model. So we are using different models for training our main model. So we will be checking which one is the best, which provides the best results of these four, and then we will be finalizing that and we will be using that for our future usage, like using in different solubility tests. And performance, similarly, we checked in boiling points. The higher the R2 value and lower the MAE value, the better the results. So, and at the end we will be checking the best model, which is random forest here, because it works best with solubility. We will be showing this in plots, like in graphs, different graphs, and then we will be using this training model, like train model, and then using random forest as our main algorithm, you can say, for this our solubility model that we have created. Then we will be using this new compounds like A, B and C, and we will evaluate these compounds, like which one is more soluble. So let's just run this file and get an idea. Okay, here you can see features we are using: molecular weight, log P, hydrogen donor, hydrogen acceptors, rotated bonds, aromatic rings, and our target is log solubility. We got this list of 20 compounds, and here if we go to the top of this file, and here you can check this, we mentioned this 20, and if I increase this to 200 and rerun the file, okay, let me just clear it and rerun the file again. Here you can see we are getting results for 200 compounds. And after getting these details, solubility difference, solubility database, and to show the relationship of different ones, here let me just drag this. Here you can see the different relationship between log S and different properties: molecular weight, log P, hydrogen donors, hydrogen acceptors. And let me just close this. Okay, and there is another one. Let me just close this as well. And if I clear this and move that to 20 again and rerun this, 20 or maybe 10, and rerun this, here you can see we got the same graphs but little values, like little dots, because we don't have enough data in our data sets. So the possible results, the predictions of this model will be not that much perfect as before we were using 200. If I put it like 50,000 once, don't try this one this much on your laptop if you're using your laptop, because it may hang. Okay, so let me just close this and close this and run again. We can run from here, but I am using this so that you guys can easily see what's happening. And here you can see the more complex graphs of different relationships, because we are using 50,000 compounds to train our ML. The better training of our model using large data set, the better the results it will predict. So linear regression, and it's just like it's taking now some time because it's running 50,000 compounds. These models running different, like we have run two models for now and two more to go, and we have got the average error value and R2 for linear regression and for random forest. Let's wait for a few seconds maybe. Okay, let me pause the video as it's taking a long time. Okay, here we got the results for SVR and for k-nearest neighbors. We also got for ME and R2 values. So we have got here the graph as well. Molecular weight, feature importance for solubility. The best one is molecular weight, then log P, hydrogen donor, acceptor, rotatable bonds, then aromatic rings. So here's chemical insights, what we got from this: molecular weight, log P, hydrogen donors, hydrogen acceptors, rotatable bonds, aromatic rings. This aligns with chemical knowledge, like log P is most important after molecular weight. Affect solubility, hydrogen bonding matters. As we can see, hydrogen donors. New compounds to evaluate: drug A, B, and C, and then running our random forest model on these compounds to get what are their solubility prediction. For drug A, it's moderate soluble. For drug B, it's low solubility. Drug C, it have high solubility as it has low log P and more H bonds. It predicted these all these values using our random forest model. Here, if we go at the end, here you can see predict, make predictions, and in predictions we provide new compounds, and the new compounds are drug A, drug B, and drug C. Here you can see we are using RF model, which is random forest model. And if I click on it, and we will go to model, from models we got random forest model. Here we had 4 models, and the best one, we chose the best one, and if we change this value to another one, we will be getting some other results. Let me just show you. If I change this to this one and change this with this value and lower these compound numbers so that we can get this done quickly, and let me just run again. Here you can see we got results for 50 compounds, and then we got our different charts, different graphs. Feature importance on line 99. We are getting some error. Okay. Sorry about that. As we are using a now different model, I need to update the different the code with the relative model, because different models have different classes and different functions and methods, and I will need to update that, and we will be learning this in our classes. So this is just we got an error for that, and we will be I am not going to change out the code right now because it will take time, and we will be learning this in the session of the class in week 4, where we will be learning proper solubility with using real-time data. And let's get back to our conclusion. And about this conclusion, we have this intensive course, like this intensive, you can see the code that I have written before. It took a lot of time to write that. It will equip you with essential machine learning skills and real-world applications to accelerate research and innovation in chemistry. Okay, the key takeaway from this course is empowerment. You don't need to become a full-fledged programmer. You just need enough ML and enough Python skills to apply them to your chemistry knowledge. This course just provides bridge. It's not just making you a software engineer, a expert programmer, not even your ML expert in chemist. It's just bridging you. Like, it will just bridge you the already available models, already available Python libraries, and your chemistry compound, which are also available on the internet in different formats. We can also create them using different softwares. You already know them better than me. By progressing from Python basics to applied machine learning projects, you will build a skill set that's not only theoretical but practical. The projects you complete will serve as a portfolio pieces which you can show in your academic, professional, or industrial settings as evidence of your applied knowledge. To conclude, machine learning in chemistry which is about accelerating discovery and making smarter data driven decisions, whether it's in drug discovery and material. Drug discovery and material science or reaction prediction, ML is become must have tool for chemists. This costs you opportunity to step into that space with guided instructions. I will be waiting for you in this session, and I hope you join the session, join the course by registering on my website or through the links that I have already shared with some people. You should have in your WhatsApp, and some people have already registered, sign up on my website. And if you feel that you will be getting some benefit from me, just go ahead and register for the course. All the information already there. If you have any query, you can ask in the discussion space that I have created for ML for chemists. You can comment on any post and I will be happy to reply to you. That's all from my side in this demo. Hopefully we will be seeing you soon after I decide the date for the start of course. Thank you. Allah Hafiz. Bye bye.